Okay, time's 11 o'clock, so let's begin here. So please remember that course evaluations, you need to turn those in here today. And so what I will do right before I leave, I'll stop class about 5 minutes early, and then I'll just, I guess you could say, pass around this envelope. I will leave the classroom so that, I guess if you didn't want to put it in here, you don't see me, or I don't see you not put it in here. But I will need somebody to take this up to the department's office. Okay, thank you very much.
I have a question. So let's say...
Were you volunteering?
Yeah.
Okay.
Oh, well, so let's say I forgot my binder of Stat 992 stuff.
Sure.
Could I potentially run home after class then turn that in?
Yeah, that's no problem.
Or if you give it to Stacy and then
Yeah.
just go tell her that it's for that class.
Yeah, I wouldn't bother running home for it. Just next time, tomorrow or whatever.
Okay.
So also assignment number 4 is due tomorrow at noon. Something I wanted to make clear, because when I was looking at the assignment's due at noon tomorrow. Something I want to make clear because I don't think it is as clear as it should have been. In the assignment on problem number 2, you need to use the parallel package for this, not the for each package. And while I do say par L apply there, I should have at the very beginning say just use the parallel package. And I apologize for not saying that. I was trying to make it easy for you so that you wouldn't have to try to install any packages at all. But obviously,
You say that in part C, the first sentence, just use the parallel package.
I do?
Mm-hmm. Yeah.
Oh, I'm sorry. Okay, well,
Yeah, you say
never
it.
mind. Okay. Oh, you should be using the parallel package, not even trying for each on Crane. Okay. When I was reading over class, it's like, I can't believe I didn't say it. No, I did say it.
You did.
I just can't read very well. Are there any questions regarding the assignment?
So this is kind of regarding shell script files. So let's say we write an R script to do estimate the true confidence level and the expected length for 1, 2, 4, and 10 threads. And you construct a shell script to run it on 10 threads. Does that change anything or make anything different?
Okay, so back up a second. Are you saying you want to, in a shell script file itself, you want to do 1 thread? You want to do 2 threads? You want to do...
No, just like run the entire R script from a shell file that requests 10 threads.
I mean, you can request 10 threads, that's no problem. The key is in Slurm, your Slurm stuff needs to request 10. Okay? So that's the key. I mean, I think, if you requested only, let's say 5, and your program actually runs, or actually needs 10, I think you'll get an error in R saying, okay, you don't have all this stuff available to you.
I guess what I'm trying to get at.
Okay.
So is it common practice to construct these so you run on 1, 2, 4, and 10 threads? Just use one R script for it? Or?
Okay. So at least the way that I did it was, just to make everything compact, is that I wrote one R program where I had my code for 1 thread, 2 threads, and then I used one shell script file that requested 10 threads. So obviously when I only needed 1, I had extra threads available to me that I didn't need.
Okay.
But I just did that because it was easier for the assignment. Now, obviously in practice though, you're not going to be looking at, well, what happens with 1 thread? What happens with 2 threads? You're just going to pick, okay, I'm going to use 10 threads. Okay?
But when you do that, it's like a different time. Because if you want for 1 thread, you want for 2 threads, you add the time over for the 1 thread, 2 thread.
Well, I mean, 2 threads is going to take less time than 1 thread.
Yes, but the time that you will give them will be the time for the 1 thread plus 2 thread for the difference. So you have to do the difference to find the time for the 2 threads.
Well, so like what I did with my own program was I for each time that I did a different set of threads, I just recorded the time. So I did like proc.time right before I did 1 thread, found the time. then a new proc.time right before I do 2 threads, then find the time.
So you essentially have the proc that time 4 times.
Yes.
Right.
Yeah. Yeah.
And you want all of our code that we're running in Crane in this, in addition to the table, correct? Like the swarming file and
Yes.
everything.
Yeah. I mean, I think you should be able to run, do this compactly. Because I mean, if you're doing everything completely separate for 1 thread, everything completely separate again for 2 threads, well then you're just duplicating a whole bunch of stuff. You know, at least in my answer key, I try to do everything rather compactly, so I'm not. While there was a significant amount of code being given, it wasn't that bad. Is there another question?
Yeah, so should we expect the true confidence level to be the same when running it in 1, 2, 4, and 10 threads?
For the non-bootstrap intervals,
Okay.
because you're
yeah.
using exactly the same data. The bootstrap intervals, because you're taking different resamples,
Yeah. Okay.
but you should still expect the bootstrap ones to be similar.
Yeah.
If they weren't, then that would be a sign that something's going wrong. Are there other questions? Okay. Let's see now. So assignment number 5, once I get assignment number 4 graded, I will post assignment number 5. Also, the numerical differentiation video lecture, were there any problems? Oh, well, first of all, were there any problems with viewing the video? Okay, good. What's your question?
Well, it's about the notes, so
Okay.
are you?
Yeah, that's fine.
On page 8, when you did, save 3 and you used the default settings for the f-derive function?
Excuse me, sorry.
No, you're fine.
Okay, page 8.
Save 3 when you're using the default settings?
Yes.
I was just wondering, when f-derive finds h on its own, is there a way to find out what it uses for h? Like what it ends up finding?
Well, I
h
believe if
in?
you actually execute the code that's after the after the comment, I believe $machine $EPS,
Oh, okay.
you could actually execute that and it would be like 10 to the negative 16
Okay.
or something like that.
Okay.
I don't remember exactly what it is.
Okay.
Yeah, I don't know. I guess maybe also it would automatically return to you inside the save. No,
No,
I don't
it
think so.
doesn't, because I was
Yeah.
looking, like, trying to find objects within save 3 and it doesn't
Yeah.
have anything, so.
Yep.
Okay.
Other questions? Okay.
In the assignment 4, part 2, if I using some source file, do I still need to pass all my source file? Like I define another 4.2 function in another file. I need to extract this file.
So I think you're talking about, for example, the way that I used the parallel package in class was I had a separate R program. Yes, I want to see that one too.
Okay.
Are there any other questions? Okay. So next what we're going to do is numerical optimization. This is going to be another one of those topics where some of you will have a lot of experience, some of you will not have a lot of experience. I would anticipate most of you have not done it in R, so even if you have done, even if you do have a lot of experience, you probably don't have it with respect to R. I would imagine too, well I shouldn't say I would imagine, I know in Stat 971 you at least get a little bit of exposure to some of this stuff. At least from my discussing this with students who take 971 in the class, I think there's at least, I think there's enough new stuff in this to make it worth your while. So this is, I should have called this numerical optimization. I just call it optimization. I'll change that in the future. And, you know, what we're going to be doing is we're going to look at what inputs to a mathematical function lead to that mathematical function being maximized or minimized. This is a very, very common thing that we do in statistics. You know, the number one place where we do this is probably with maximum likelihood estimation. Very often when you want to do this, basically you need to find, let's say, a new mathematical function based upon your original mathematical function. And you need to, with this new mathematical function, you need to set it to equal to 0 and then solve for these inputs that maximize or minimize the original function. So for example, with maximum likelihood estimation, you know, you take the derivative of the log likelihood function, set it equal to 0, solve for it, then your parameters to get the maximum likelihood estimates. And so you're often working with estimating equations. You know, estimating equations are used a lot in statistics, not just with maximum likelihood estimation. And basically an estimating equation is some kind of equation where you set it equal to 0 and you solve. Now, optimization itself, in terms of the research area, well, that's more of an applied mathematics area rather than a statistics area. And while statisticians have contributed some to the research aspect of optimization, statisticians are essentially more users of research that's already been done out there. And so because of that, I take that point of view then in introducing you to optimization. So there's going to be a number of examples here that are very simple, that you can do the optimization essentially by hand, stuff that you would have done like in Stat 883. I purposely put these examples in here because that allows us to do some comparisons, because we'll be able to do it by hand in terms of just analytically drive something, and also we'll be able to do it numerically by using the computer to do that. And I think that's always a very helpful thing to do in any kind of learning setting. So one of the examples that we're going to be looking at is something that you did in 883, maximum likelihood estimation for the probability success parameter pi that corresponds to a Bernoulli distribution. So let's say that we observe a random sample of Bernoulli values, y1 through yn, and we want to know what's the maximum likelihood estimate of pi. And so what you would do in Stat 883, of course, let me get my red pen out. Define your likelihood function. Of course, the likelihood function is a function of your parameter given your data. So I put my data into a vector, call it y, and it's just the product of all my possible Bernoulli distributions from for y sub 1 through y sub n. And I can simplify it, of course, a little bit so that now I just have the number of successes. That's often what you refer to as y equal 1s for Bernoulli random variables. Number of successes is w, and the number of failures is n minus w, so a number of y equals 0s. So that shouldn't, this should be familiar. And you learn that pi hat, the maximum likelihood estimate, the thing that actually maximizes this function here, is simply the observed number of successes, w divided by n. What we're going to be interested in learning about, well, how would we actually do this in a numerical manner? Well, one of the simplest ways to do this, and I think sometimes students forget this, and that's why I like to point it out, is that you could do a very simple search algorithm where you just, you know, calculate, let's say, the likelihood function for a whole bunch of possible values of pi, and look at, well, what value of pi actually maximizes that likelihood function. Very, very simple. Now, in practice, you typically wouldn't do this, but where this can be very useful to do is when you are doing statistical research and you're maybe applying some more complicated numerical optimization method, and you want to check, well, is this actually working? Is it actually finding what it needs to find? And so simple search algorithms in that stage of research can be extremely helpful. So let's look at simply how we would apply it in this particular setting with the Bernoulli distribution. So my R program, mle_Bernoulli.R, contains all my R code. And similar to what we had saw with the numerical differentiation notes, let's let W equal 4, number of successes is 4, and we have 10 trials. And then my log likelihood function, of course, is just W times log of pi plus N minus W times the log of 1 minus pi. Okay, so and we've already seen some of this in the last set of notes. I wrote a function, I think this is new, I wrote a function to actually evaluate the likelihood function itself. Also, I wrote a function, this was in the last set of notes, that evaluates the log likelihood function. And then I just do some plots. So here are two simple plots. On the left we have the likelihood function, on the right we have the log likelihood function, and we can see, well, what value of pi actually maximizes it. Obviously it should be 0.4, and indeed that's what it shows. So then a simple search algorithm then would do something like this. How about I create a set of pi's that I'm going to search over, maybe 0.3 to 0.5. It seems reasonable. I'm going to go by 0.01. And I simply create a data frame that has all my values of pi that I'm searching over. And then I'm going to evaluate my likelihood function at all those values of pi. Again, taking advantage of how R does its vector-based calculations. And then I do the same thing for the log likelihood function too. And then it's just a matter of looking at, well, where does this maximization happen? And of course, it happens at pi equal 0.4. So we can see that indeed these are the maximum possible values of the likelihood function, log likelihood function, just from a simple search algorithm. Okay. Page 4, I talk about just a little bit of a different way to write your functions. You can take a look at that on your own. Now we can also then perform function maximization by first finding the partial derivative of the log likelihood function with respect to pi. And we're seeing that in the set of notes from last time. W over pi minus N minus W over 1 minus pi. Set this equal to 0, solve for pi. I believe we did a simple example with the uniroot function last time with that. And so, again, I have the same function as what we did before for the first derivative, where you can actually program it in. And then I just evaluate it with the curve function. And you can see that indeed, when that function is equal to 0, pi is equal to 0.4. So nothing really new there. And once again, you can do a simple search over all these values of pi from 0.3 to 0.5 by 0.01, and you can see that indeed when pi is 0.4, the log likelihood function, the derivative of the log likelihood function, which for some reason I just call it L, is equal to 0. Okay, nothing too complex there, but it's just a good reminder of a simple way to do some of this stuff. Okay, now one of the things when you have to watch out for when you are maximizing a function or minimizing a function, trying to figure out what input causes that to happen, is you have to what we have to watch out for are what are called local minimums or local maximums. What you want is what's called the global maximum or global minimum. And more sophisticated search algorithms are not necessarily guaranteed to find the one value of the input that gives you the overall global, the overall maximum of a particular function. They're not guaranteed to. Instead, again, what you might get is a local one. Well, what do I mean by that? Well, we can talk about that in the context of what are called convex functions. And we just simply have, let's say, one function, we'll call it f of x. Just think of it in a mathematical context, not necessarily a statistical one. And this function here, this drawing here, is convex because if I pick any 2 points that lie on that line. I can do a straight line between these 2 points, kind of do a straight line there. And it's always going to be, in this case, below the line, the function itself. So because of that, we say this is a convex function. When you have convex functions like this, these numerical search algorithms, generally speaking, will always find the value, let's say, of x that's going to maximize f of x. The problem, though, that you run into is sometimes functions that we deal with, though, are something like this, which is not a convex function. So if I take any 2 points, maybe I'm going to take a point, let's see now. Let's see, maybe there and there. And notice if I were to connect them with a straight line, I have to actually go over that function itself. Because of that, that's not a convex function. And what can happen with these search algorithms is that when it's trying to find the maximum, which occurs right here, it might get caught over here and all of a sudden declare that the maximum actually occurs here. And because of then that's called the local maximum, not necessarily a global maximum. Excuse me. And so you just got to realize that these search algorithms are not perfect. Okay. So the main search algorithm that statisticians use is the Newton-Raphson method, which I bet, even in Set 971, I'm sure you talked about that some, right? And various, and some variants of the Newton-Raphson method that statisticians use. Now, there are many other search algorithms out there. We're just going to focus on these in this particular class. I had hoped at the beginning of the semester that we would have more time to talk about some of this other stuff, but unfortunately we don't. A good reference on some other ones is the book, the Houghton and the Givens and Houghton book. That was a recommended book for this class. They talk about some other algorithms in there. Okay, so what the Newton-Raphson method does, it tries to find an x such that f of x is equal to 0. In other words, it's trying to find the root of the equation. The reason why that's important for us is because, again, like with the log likelihood function, or with maximum likelihood estimation, we take the derivative of the log likelihood function, set it equal to 0. So we're finding a root. So that's why the Newton-Raphson method is so important. And let's make sure you understand how this Newton-Raphson method comes about. Okay, all has to do with Taylor series expansions, and Taylor series expansions are all over statistics. So let's say that we try to approximate f of x by a first order Taylor series expansion. So what that means then, and we're going to expand about x0, so just some point x0. So then f of x then is approximately f of x0 plus the first derivative of f of x evaluated at x0 times x minus x0, and you could divide by 1 factorial if you really wanted to. And so that's that's an approximation to what f of x is. This is actually a linear approximation. Notice how just x is in there. You don't see an x squared or something like that. And and this will be helpful for later on, we can rewrite our equation then as f of x0 minus x0 f dot of x0 plus x f dot of x0. I'm going to highlight that right there. So we can see that essentially this is like the y-intercept of a line that you will learn about in your old algebra class. Let's call it a. And then we can see that the slope of the line is that first derivative evaluated at x0. So the line y equal a plus b times x is essentially represented there. Excuse me. Now, of course, if f of x then originally was just a linear function of x itself, then this approximation would be perfect. I mean, it wouldn't actually be approximation. Now, what we would like to be able to do now is, again, we want to find the root of this equation. We want to find what x is going to make f of x equal to 0. So, especially if you have a very complicated function f of x, what's easier is work with this approximation. Set this approximation equal to 0. And then, what I do also is I replace x with x1. You'll see why I do that shortly. And I simply solve for x1. And what that's going to give me is the root of this particular equation there, and this is going to actually be a better approximation to what the actual root here is in f of x is equal to 0. So let me come back down here. So x1 then ends up being equal to x0 minus f of x0 over the first derivative of f valuated at x0. And so what this, again, this x1 is representing essentially well, let me back up a second. This x0 here, what we expanded about, you can kind of think of that as maybe an initial guess to what the root is of the f of x equation. And then x1 actually represents a better estimate. And so what the Newton-Raphson method does, it basically kind of repeats this process of trying to get a better guess or better estimate over and over again. So what we can do is use x1 then in the same role as x0 before, so that we can come up with a x2. And so that x2 then is equal to x1 minus f of x1 over that first derivative of f evaluated at x1. And so again, what the Newton-Raphson method does, it just repeats this process over and over and over again until we get to a point where these better guesses that we're getting are not really changing much. And so that's when we say we have convergence. More formally, you can say, let's say at the rth iteration, or r plus 1 iteration, look at the difference between x of r plus 1 and x of r. Look at the absolute value of that difference there. If it's less than epsilon, for some epsilon greater than 0, that's quite small, then you have convergence. Okay. So let's look at a simple demonstration of this graphically. So this gets back to then the function that we looked at in the numerical differentiation section. F of x is equal to x cubed minus 5. And what I'm interested in doing is finding the root of this equation where I'm going to look at over the range x equal 1 to 4.5. The first derivative, of course, is 3x squared. And so, let me just page down here. So if we just focus on the red line, we can see, well, where is that root? That's right there. So it's about 1.7 or so. And we like to be able to find a way to numerically find that. So to do this in R then, and this is more for demonstration purposes rather than what you would actually do in practice, because we'll have nice little functions that do this automatically for us. What I'm going to do is define a function called fx, like I did before in numerical differentiation section, which finds x cubed minus 5. Also, I have f dot of x as well. And notes here. What I'm going to do is set up a function that allows us to see this actual f of x approximation that we have here. So this is going to be like our f of x 0. And this is going to be our x0 times f dot of x0. And this is going to be our f dot of x0 times x. Notice we're taking a subtraction there. And so, of corresponding to what I had written out before. This is like our a for y equal a plus b times x. And this is going to be essentially like our b there. Also, I'm going to create a function called x dot val, which actually goes ahead and finds, for example, say x1 is equal to x0 minus f of x0 divided by f dot of x0. And then I have some color choices that you'll see why I do that shortly. Okay. So let's say that I initially guess the root of the equation to be 4. So this is like x0. Take a look at my plot. What that is saying is I think the root of the equation is 4. Obviously that is incorrect. And what we do with the Newton-Raphson method then is we try to find a linear approximation to our red curve. And so, similar to what I had written before, here's our a, and here's our slope. And I use the AB line function to actually graph that linear approximation. So you can see in what's called goldenrod, which goldenrod is it? I think goldenrod 1, that color, in R. We see a straight line there. That's our approximation to the red line. And what the Newton-Raphson method does is it says, okay, well, let's set this approximation equal to 0, solve for where the root of that equation is. And that root is right there. So because of that, that becomes our x1. Again, we're looking to be right here, though. So we can see, again, we have an improvement, but it's not as good as we would like it to be. Okay. So, excuse me. So this x dot val function, as I mentioned before, it allows me to, given, let's say, x0, allows me to find x1. And that value ends up being, let me actually come over here. Oops. Okay, I'm going to rerun some of this stuff. And that value ends up being 2.77. And just again for illustrative purposes there, I took my fx.app function, which does this linear approximation. I plug in there what what that 2.77 is, and you can see that indeed I get a value of 0 back. Okay, so you can say, well, that's iteration 1 of the Newton-Raphson method. And iteration number 2 says, okay, well, let's find now a better linear approximation to that my original f of x equation. And so this is what I get then. So this line right here then represents my newest linear approximation. And what we try to do is, well, let's set that equation equal to 0 and solve for the root of the equation. And now we can see that the root of the equation is here. So I'm getting closer to where I need to be. And that value ends up being 2.06. And so in my program here, I keep on doing this for iteration, let's say 3, iteration 4, 5, 6, and eventually it leads to the plot that you see on page 13. So all the straight lines there are my linear approximations, and my goal was to get a darker color for each iteration. So the iteration 6 then would be the darkest color of all. And we can see that that linear approximation then eventually gets to a point where indeed you're right at where the root of the original red line was. So that's how the Newton-Raphson method works. Again, I anticipate that it is not necessarily new to some of you, but I think it's at least, it gives us a good place to start. So we're all at the same level now. Are there any questions? Okay. So, again, where does the Newton-Raphson method come into play for statisticians? And I've kind of already said this before, is that, with maximum likelihood estimation, for example, we're trying to do a linear approximation to the log likelihood function, the first derivative of the log likelihood function. And so what we're doing is we're using that Taylor series expansion again, where we're expanding about, let's say, theta 0. And that would typically be, let's say, your initial guess to what the maximum likelihood estimate would be. And then through using the Newton-Raphson method, we could get successively, hopefully, better estimates. And this is what then the Newton-Raphson method then looks like applied in a log likelihood function situation. Notice how the second derivative of the log likelihood function actually comes into play. So of course, if you want to implement this, you need to make sure a second derivative, in addition to the first derivative, of course, exists. Yes?
For the previous example which we did,
Yeah.
the tangent lines, so how did we check the convergence? We did not.
I guess maybe I did not. I mean, obviously you can solve it by hand, and I did not because you could do it by hand.
So do we just put in like x dot guess minus whatever was?
Yeah. So let's say let's just do this real fast. So I had 1.709 there, and let's do it one more time. And notice how close they are. So you could just simply subtract the two.
Is the fx dot approximation giving us?
What that's giving you is for the linear approximation itself.
How much?
It's looking at basically just showing you indeed that you did get the root.
0.
Okay.
I was kind of thinking if we can plug in something which will iteratively do the subtraction and have a convergence criteria.
We will actually do that later.
Okay.
I think even with the next example. Okay, so let's actually look at maximum likelihood estimation with the Bernoulli distribution. And again, we know what the maximum likelihood estimate is, but this is how you would do it in a numerical manner. So again, we'll know where we need to get to. So in this particular setting then, our parameter is pi. So let's say at the r plus 1th iteration, we're looking for pi sub r plus 1. We set it equal to what we had in the previous iteration. We subtract off the first derivative of the log likelihood function, evaluated at pi sub r, and then we divide by then the second derivative, evaluated at pi sub r. And so, we've already done the first derivative. You can verify that indeed that I did get the second derivative correctly on your own. And so this is how the Newton-Raphson method would work here. So let's say my initial guess for the maximum likelihood estimate, we'll call it pi 0, is actually equal to 0.3. I'm going to use my convergence criteria of epsilon be 0.0001. And in order to save my results, while you don't necessarily need to do this, I like to save my results at every iteration so you can see what happens. I create an object called save.pi.hat. And it's going to be equal to, you'll see how I change this throughout. For now, I'm going to just set it to my initial value of pi.hat. And I'm going to write a little loop here to continue with doing these iterations until I get convergence. So I'm going to check, is the absolute value of, and you'll see what changes shortly, is my absolute value of change, which represents, well, how much is my pi changing from one iteration to the next? Is that greater than epsilon? If it is, then do all this. If it's not, then stop. You've reached convergence. Now, to start the loop, though, I need to define what changes at the very beginning. So I'm going to just set it to a dummy value 1 that is greater than epsilon to make sure that indeed that I can actually enter the loop to begin with. Okay. So Here's my while loop. And what I need to do, again, is program in pi sub r minus the log, the first derivative of the log likelihood function over the second derivative. So here's my numerator. So this right here is going to be num. My denominator, this is this right here. And then once I have that, I take my pi hat that I started off with, and I subtract off num divided by din, and I get my new pi hat. So this is essentially pi r plus 1. Then I calculate change, which actually calculates my new pi hat minus my original pi hat, or what I had started off with, you could say, at least the first time through. And I calculate my change. Let me do some erasing here. Then next, I put in what I got for my new pi hat. I'm going to then move that over to what my original, you can say my original pi hat is. That way, when I go through my next time through my loop, my pi sub r is going to be what was pi sub r plus 1 on this time through the loop. And then lastly, I keep track of all my pi hats that I'm creating, or I'm finding through this looping process by putting what I had for my pi hats, my save.pi hat, notice that's right up there, and then whatever that pi hat that I just found goes into there. So this whole process then continues until the absolute value of change is is less than epsilon. Didn't necessarily explain it the best way. If there's any questions, please feel free to let me know. Do note that whenever you have a loop like this, what can you do to see what's actually occurring? Well, put some print statements in there, and so that every iteration you can see what's actually updating or what's happening. So after I run that, then I use a data frame where I have the number of iterations and all the pi hats that I created throughout the iterative process. I print them all out. And you can see how that it takes up to iteration 5 before I get to 4. And note that if I were to subtract these two, it's going to be less than 0.0001, which is what I set my epsilon to be. So it's not too difficult. Just out of curiosity, I did some plots that help demonstrate this whole process. And so in the top plot, you see just the likelihood function itself. And you can see with the open circles, those corresponds to my actual pi hats that I'm getting through the iterative process. You can see that I'm reaching up to the max. And then also you can do the same thing with the log likelihood function too, just for demonstration purposes. And then lastly, on page 17, somewhat similar to what we saw with that f of x is equal to x cubed minus 5 example, I actually do some, excuse me, I plot the line that, or the function that we're essentially finding the root for. So the black line represents the first derivative of the log likelihood function. And then at the very first iteration, we basically find what's actually called a tangent line to it at pi equal 0.3. And so then if I find the root then of this tangent line, this linear line, you can see that will be your second iteration's estimate of pi, or what will actually be pi 1, which is 0.384. And you can keep on drawing those linear lines corresponding to that the first derivative of the log likelihood function until eventually you're right where you need to be. Are there any questions? Okay, well, what happens then if theta's, if let's say our parameter of interest is actually multiple parameters, and let's say we have maybe a p by 1 vector of parameters that we're trying to find the maximum likelihood estimates for. Well, the same process holds, but now you're doing it in a multivariate setting. So the first derivative of the log likelihood function for a p-variate case, of course, then would be a p/1 vector. And you are approximating it through this Taylor series expansion, approximating that vector with another vector, but evaluated at theta 0. And then the second derivative of the log likelihood function then is actually a matrix. It's going to be a p by p matrix. And you take it times theta, p/1, minus theta 0, p/1. This structure then of this second derivative of the log likelihood function looks like this. It's called a Hessian matrix. I would think that that should be familiar based upon 971. So you can see, for example, the 1, 1 element is the second derivative of the log likelihood function with respect to theta 1. The 1, 2 element then is the second derivative, where one derivative is with respect to theta 1, one's with respect to theta 2. Okay. So then the whole process put into this multidimensional setting, theta sub r plus 1, meaning what at the r plus 1 iteration, what's the Newton-Raphson method going to give you, is equal to theta r minus the, and that's actually should be over here, and remove the transpose. Will be the second derivative of the log likelihood, second derivative of the log likelihood function, invert it, times then the first derivative. All that evaluated at theta sub r. So that's what the Newton-Raphson method then looks at. It does all these matrix calculations. And then convergence, depending upon how you define it, you might look, for example, you could look at every single element. Oh, look at that. Let's say the jth element. You could look at the jth element to make sure that every jth element is less than epsilon in terms of the absolute value, the difference. Or you could instead do this. Where you take the square difference of all the elements in those theta vectors, add them up, take the square root, look, is that less than epsilon? If it is, then you got convergence. There's many other ways to do this too. Okay. Now, there's a number of variants to this Newton-Raphson method, especially in the sense of when you have a vector of parameters. And a lot of it has to deal with the fact that when you're doing a second derivatives, you're doing this what potentially could be a very large matrix, and you're having to actually find the inverse of it. That's where some of these computational aspects can be complicated, maybe potentially could take a lot of time, and also perhaps there could be more chances of error involved. And so one simple approach that's often used in statistics then when this happens, in these kinds of cases, is you use something called Fisher scoring. How much do you actually use the word Fisher scoring at all in 1971? Okay, good. And this is a quasi-Newton-Raphson method. It's quasi, the word quasi comes about by it's not exactly Newton-Raphson. And then what you do is you just simply replace then the matrix of second derivatives with then the expected value of that matrix, essentially, evaluated at theta 0. That's Fisher scoring. And there are many cases where Fisher scoring will end up with the same result as the Newton-Raphson method. In particular, generalized linear models when you use a canonical link function. Hopefully that sounds familiar from 1971. Now, another reason why often Fisher scoring is nice to use is because it's closely related. Calculate some quantities that are used frequently in statistics when you're doing maximum likelihood estimation. So we've seen this result before in our class, and you've seen it in other classes too, that of course if theta hat is a maximum likelihood estimate, it has an asymptotic normal distribution to it. Square root of n, theta hat minus theta converges the distribution to a normal random variable with a mean vector of 0, and Fisher's information matrix inverted is the actual covariance matrix. Fisher's information is just simply the negative of this expected value of the second derivative of the log likelihood function. Does anyone by chance know how to prove that? Prove this result? It's the central limit theorem argument. So, just a little bit of a side note. Okay, so if we're doing maximum likelihood estimation, obviously this is a very important thing to have. Also, another little important aspect too of this is that the second derivative of this log likelihood function converges in probability to the expected value of that second derivative of that log likelihood function. And so because of that, if you evaluate this second derivative at theta hat, you can use that, is often used as an approximation to that Fisher information matrix. And when people do that, that's referred to as observed Fisher information. Does that sound familiar from 971? Mm-hmm. Okay. Now, one of the, and you can see I kind of got excited there. One of the reasons why this is so important, and this puts it into context of what we did with the numerical differentiation section, is that we have automated ways to do these we have automated ways to do these derivatives, where you don't have to actually do it by hand. So if you use then a numerical derivative for this log likelihood function here, you have an automatic way that you can find then the covariance matrix to use when you're doing maximum likelihood estimation. Now the reason why I'm so excited there with all those exclamation marks is that I didn't, when I was in grad school, no one really taught me. I didn't really think about this. That that there are maybe ways that a computer can actually do these numerical derivatives for you in the context of maximum likelihood estimation. And so whenever I was deriving or developing new statistical methods and programming it in, I was actually, let's say, finding Fisher's information matrix by hand and then programming that in directly into R. Or I would work with the observed Fisher information, essentially find it by hand and then program it in, I should say R, program into S+, or SAS even. And then I was doing some research, and I got a program from another researcher, because you can simply let me back up a second. There was actually it was a 2000 biometrics paper, and I contacted the author and said, hey, could you share with me your program that you use to do some of these calculations? And he said, sure. He emailed it to me, and I saw that instead of actually programming this stuff essentially by hand like I was saying before, he was just simply using S+ to numerically differentiate everything, and that's how he got his results very easily. And when I saw that, I was like, wow, this makes my life a lot easier. Perhaps you already knew to do that, but if you don't worry, I will show you how to do this shortly. So what do you choose then as an initial choice for your maximum likelihood estimates? In other words, your theta 0. Well, you could use, for example, maybe method of moments estimates, or you can use MLEs from a simpler model. So let's say if you're using this kind of stuff to estimate a logistic regression model without using, let's say, the GLM function or procgenmod in SAS, you know, what could you do? Well, you could simply maybe do a normal linear regression model, get your estimates for your betas out from that, plug that in as theta 0 essentially in the Newton-Raphson method, and then use it to find the maximum estimates. Obviously some problems, well, of course, for example, there may be more than one maximum in terms of what I was talking about with respect to global and local. Okay, so let's talk about R functions that are available for this to automate this process. There is a whole CRAN task view on this kind of stuff. I urge you to take a look at it. What we will do is focus on the optim function. I've used this function for, well, since the example I was telling you about that biometrics paper, that's when I first found out about it. So I've been using this now for about 14 years or so. And it really makes your life really easy. It's very slick. How many of you use Optim before by chance? Okay, one. It's very nice. So it basically implements a variety of different optimization methods. It doesn't do Newton-Raphson exactly. It uses some quasi-Newton-Raphson methods. But it also gives you some other optimization methods that you can use as tools. And what's really cool about it is that all you have to do is give it the mathematical function that you're interested in. That's it. It does all the derivatives for you numerically. You don't have to specify any derivatives yourself. You can if you want, and that might help with convergence, but I don't think I even have had an occasion, at least in my research, where I've needed to. Also, it automatically will then give you an estimate of the Hessian matrix, with respect to which, if you're using for maximum likelihood estimation, that's the second derivative of the log likelihood functions, and then that can be used then for to get your covariance matrix. So it can be very, very helpful. Interestingly, though, this function actually does minimization, not maximization. So if you're using this for maximum likelihood estimation, well, instead, why don't you minimize the negative of your function of interest? Because that will allow you to get the maximum of the function of interest. Okay, so let's take a look at an example here. This deals with the gamma distribution. Have any of you ever found the maximum likelihood estimates for a gamma random variable? Well, in 883, you probably didn't do it because there's not a closed form solution. Did you by chance ever do it in 971? Maybe you had a gamma regression
We
model.
did in 883, but we only found like the one. And then we said beta can't be found by hand. You need to use some
Okay.
optimization. So we talked about it.
Okay, well, that's good, that's good. Well, here's how you can do this in a numerical way. We did a little bit of the gamma stuff already in the numerical differentiation notes. So there's the likelihood function, there's the log likelihood function. And similar to what I said in numerical differentiation notes, while these are the kind of the simplified forms, often in programming, aspect, it's actually easier not to simplify it as much. And you'll see that shortly. So if I want to find the maximum likelihood estimates for alpha and beta for the data that we saw with the numerical differentiation section. And so I need some places to start. I need alpha 0, I need beta 0. And so MOMs, or method of moment estimates, are a good place to do this. I bet you can find the MOMs in 883. So if you remember, for a gamma random variable, the expected value of x, or expected value of y here, I'm using y, is alpha times beta. So I'm going to set that equal to y bar, essentially the sample estimate. And then the variance of a gamma random variable is alpha times beta squared. I'm going to set that equal to what I call s tilde squared, which is the usual bias estimate of a variance. Is everyone comfortable with me using that? Okay, because sometimes you're taught, well, you should use the second moment. Expected value of x squared, find that, set that equal to, let's say, 1 over n times the sum of the y squared. You could do that, or what's often easier is just to use the variance instead. And notice I'm not using the unbiased version. So then, it's just a matter of solving for alpha and beta. You got two equations, two unknowns, and here are the moms. This is my same simulated data from the numerical differentiation section. Something I did not include in that section was histogram, EDF plot, and QQ plot of the data. And I actually plot with it the actual gamma distribution. Remember, I have a sample size of 30. So what do you think? Do you think the data follows that distribution? This is just kind of a side note here. And this is where it's a great example of you can't be too picky. Okay? I have a sample size of 30. It's right skewed. This is the right gamma distribution. The data comes from the correct distribution, but if you just gave this to someone without saying anything about the sample size or what the true distribution is, they might be thinking, oh, wait a second, I see a big deviation there. Oh, look at that. Wow, that misses where the peak is. Ew, this isn't good. But this just shows you have to be careful with using these kinds of tools to make judgments about distributions. Even a sample size of 30 is not good enough to make a good judgment about the gamma distribution here. Okay, so let's look at the optimum function. The first thing that you need to do is write your own function that calculates the mathematical function of interest that you want to maximize or minimize. And so I wrote a function called log L. And in fact, we did this in the numerical differentiation section, where I have two parameters. I'm going to put them into one vector, call it theta, and then also I'm going to pass in my data. That's going to be in y. Do note that when we use the optimum function, the first element of this R function that you're writing to represent a mathematical function has to correspond to your parameters that you're essentially maximizing or minimizing over. And it has to be one vector. So I can't have alpha, comma, beta. It has to be everything's in one. And again, remember how I actually then write out the log-like function. In the end, I take the sum of d gamma, where I use the log equal true argument. And that's the quickest way to do it, best way to do it, in fact. I find my method of moments estimators, alpha and beta, for alpha and beta. So I get 3.35 for alpha and 2.35 for beta. And now I get to the optimum. So I say optimum, my parameters of interest in the par object, or argument, excuse me, and I put in there my starting values. So this would be essentially alpha 0 and beta 0. For Fn, that stands for function that I want to minimize. I want to minimize log L1. Then, since there's a dot 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 argument in optimum, I can specify, oh, that I need my y also in log L1. Then the method that I want to use for optimum is going to be BFGS, which stands for Broyden, Fletcher, Goldfarb, Shano. Basically, this is just a quasi Newton-Raphson method. It does some stuff with the derivatives that it needs in the Newton-Raphson method. A little bit different from what Fisher scoring does. But it does some stuff to make the derivatives a little bit easier. If you really want the details, take a look at the required book for this class, and also the Gibbons and Houghton. I decided not to go through those details because, again, statisticians are primarily users of optimization, and I didn't think it was necessarily worth our time, especially given where we are in the semester, to go through those details. Now, the control argument allows you to control various aspects of the process itself. And the only one that I ever use, not typically, there's one other one I sometimes use, but this is the main one that I use almost every single time, is FN scale. This argument came about, probably about 10 years ago, because people were kind of frustrated at the fact that optim minimizes a function, when in statisticians often want to maximize a function. And so FN scale stands for, let's scale my function by -1. So in other words, it's going to take -1 times whatever log L gives you. So that while I am minimizing the negative of log L1, that means I am actually maximizing log L1. So it's a nice little option that was added. And then lastly here, Hessian equal true. The default is false. I want my Hessian matrix so I can get my covariance matrix. So again, notice here I am not telling R anything about derivatives. It's going to do everything on its own. So I put the results into gam.mle1. I get returned to me a list, and here is my maximum likelihood estimates. Alpha hat and beta hat. So you can see they are a little bit different from what the moms were. The minimum value of this scaled function that I am trying to minimize is -84.8. We have some information about the iterative process. Don't worry about that. What you do need to worry about, though, is the convergence. That's 0. That's a good, you want 0. You might be thinking, oh, I always want 1. No. Here you want 0 because that says you have converged. 1 means you have not converged. And there are actually some other things that can be printed there too. You can take a look at the help if you're interested. And then lastly, we have the Hessian matrix. So this is actually then the second derivative of log L. Oops, I didn't even do the second derivative there. Okay. Now, to find the covariance matrix then, remember we have to take a negative of it. So I'm going to do the negative. And then to do an inverse in R, if you've never seen it before, it's the solve function. And I pull out Hessian from gamma.mle1. I put that into cov.mat. So for example, the estimated asymptotic variance of beta hat is 0.594 using basic maximum likelihood estimation results. Here's the estimated asymptotic covariance between the two statistics. And I can put this all into a nice little data frame here, similar to what you often have for the output for, let's say, fitting a regression model, for example. I have the estimate and the standard error. So the square root of the estimated asymptotic variance. Okay. Let's make sure that I talked about everything. So what we're saying is that the maximum likelihood estimators have an approximate bivariate normal distribution to it. How could I use this information then to find a confidence interval for, let's say, beta? Perhaps it's just too easy. Suppose I want to do a walled interval.
estimate and then
Plus minus.
use
Yeah.
the square root of that?
Yeah, so 2.8744 plus or minus 1.96 if I want 95% intervals times the square root of 0.5944. There's your Wald interval. Yeah.
Why are we using the method of moments as like the initial estimates again? Like, is there anything
Yeah,
special about them?
we just need some place to start, and that just seems like a reasonable place.
Okay, so technically it could be any value.
Yep.
Just the iterations. might
Just realize though, if you take, let's say if you decided to take 1 million as a value for beta, you might not get convergence.
Okay.
And the next question is not necessarily where to the best. And I just simply, I want you to ignore the numbers that are up here for the next question. And that is, how can we use Monte Carlo simulation to examine if a bivariate normal distribution, as calculated through maximum likelihood estimation theory, how can we determine if a bivariate normal distribution is actually appropriate at n equal 30? This goes back to the first section in this course. It has nothing to do with true confidence levels or sizes. So how about you simulate some more gamma data. Suppose you do R equal 1,000 simulated data sets of n equal 30. Each time, apply the optimum function to get the maximum likelihood estimates. Okay. Get the Hessian matrix. Get that covariance matrix out. And then what you could do is just simply, examine, well, based upon what you see with that data, just like what we did in the Monte Carlo simulation section, you could use all that information across 1,000 simulated data sets to determine, well, indeed, is the normal distribution appropriate? So the very simplest thing you could do is do a plot of all your alpha hats, okay? And does it look like it follows a normal distribution? That's how you would do it. Okay, so we are out of time because I want to allow you to put the evaluations in this envelope here. So what I'm going to do you have a question?
Yeah.
Yeah.
So we're gonna get to numerical integration next
Yes.
on Thursday, right?
Yes.